We can identify our acids by how many acidic hydrogens they have. So the acidic hydrogens, being protons when they come off as an ion, are called protic. So if they have one ionizable proton, it's monoprotic acid. 2 will give us diprotic. 3 will give us triprotic. So in our inorganic acids, we have 2 categories: binary acids and oxyacids. Binary acids is hydrogen with a nonmetal element. So the examples here: hydrochloric acid, hydrobromic acid, hydroiodolic acid, hydrofluoric acid, hydrosulfuric acid. And in all these examples, we see that hydrogen is the first element. Now we have water, H2O, with hydrogen as the first element. This is the one example where hydrogen is listed first, but it's not an acid. Water is neutral. It can act like an acid or a base, but it's neutral by itself. And then if hydrogen is listed second, as in ammonia, that is a sign that this is not an acid, will not behave like an acid. Now a larger list of acids would be the oxyacids. Oxyacids start with a polyatomic anion, and then we neutralize the charge on the anion with our protons, our hydrogen ions, to give us a neutral acid, neutral oxyacid. It's called oxyacid because the polyatomic anions consist of an element with oxygen and then a negative charge. So the examples down here, we have SO4 is sulfate, which has a 2- charge, so 2 hydrogens will neutralize the charge to give us sulfuric acid. PO4 is phosphate with a 3- charge. 3 hydrogens neutralize the charge to give us phosphoric acid. Inorganic acids, also called organic acids, also called carboxylic acids, have a COOH group on them. This is the carboxylic acid group. Depending on how we write the compound, it might not be completely obvious to us, that COOH. Just have 3 examples here, 3 of the smallest organic acids. So the middle one, CH3COOH, is our vinegar, which we use as a flavoring agent and also as a food preservative. First one, formic acid, only has a single carbon. This is our smallest carboxylic acid possible. And this is a bitter agent, bitter acid, that's used by some ants as a defensive chemical weapon. Next one up in size would have 3 carbons, propanoic acid. And there's a really large, unnumbered, limitless group of organic acids. We list our acids as either being strong or weak. A strong acid is an acid that will dissociate essentially completely. And generally it's disassociates so completely that we can't measure the undissociated component. A weak acid is an acid that only dissociates partially. So it's not a complete ionization, and we can measure a unionized portion of the acid. So our strong acids, we have a short list of strong acids: nitric acid, hydrochloric acid, hydrobromic acid, perchloric acid, hydroiodolic acid, and sulfuric acid. These are our strong acids. These are all strong enough that we can't measure the unionized component. They're not all the same strength, so when we start to combine these acids, we can still designate some as being stronger than others. 2 of these acids are different from the rest. So hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acids are generally just normal acids. Being normal acids, they cannot dissolve copper, gold, silver. But two of the acids, nitric acid and perchloric acid, are oxidizing acids. This gives them a second ability to react, which we'll be looking at in terms of the next category reactions, the redox reactions. So we actually use perchloric acid as rocket fuel because of that oxidizing ability. So it's an oxidizer in addition to being an acid. And also nitric acid is used as an oxidizer, and it can make many compounds to be explosive because of that oxidizing ability of the nitric acid. And nitric acid, because of its oxidizing ability, can dissolve copper and silver and gold, because in that case it will be oxidizing them, not just dissolving them as an acid. Our bases, again, we can identify as being strong or weak. Strong bases dissociate in essentially completely in solution at a sufficient concentration or solubility. Weak bases dissociate only partially in solution, or they have a low solubility. So our strong bases are going to be the soluble hydroxides. So again, we have a short list here of 6 of our soluble hydroxides. So lithium hydroxide, strontium hydroxide, sodium hydroxide, calcium hydroxide, potassium hydroxide, and barium hydroxide. So we're seeing that we have the alkali metal hydroxides and the heavier alkaline earth metal hydroxides. Now the other metal hydroxides, remember the solubility rule for hydroxides. Hydroxides are generally insoluble. So the other metal hydroxides are not strong bases because they are low solubility. And then our ammonium and amines are weak because they only partially ionize, partially react with water in solution. So both acids and bases are corrosive compounds. They can corrode through skin, burn our skin. They can corrode through clothing. They can corrode through metal. A common problem in the old days before we started to get wise is that companies would put 55-gallon drums of a acid or base out in their back lot. 55-gallon drums were the common way of moving moderate volumes of liquids around. They might come back in a couple months and find the drum empty, find that there's a couple holes in the bottom of the drum. The acid or base ate through the 55-gallon drum and then leaked out into the environment. But if we take that acid and base, mix them together, we get something that is non-corrosive, something that cannot eat through metal, cannot eat through skin. We actually get salt water. But salt is a generic term for ionic compounds. So our example here is a sodium chloride, which is table salt. But salt is this generic term for ionic compounds. But we get salt and water as our two products. So if we do hydrochloric acid and sodium hydroxide, we get table salt and a sodium chloride and water as our products. For these Arrhenius acid-base neutralization reactions, the net ionic equation, the actual reaction that is occurring, is the hydrogen ion is reacting with the hydroxide ion to form water. So that is where the ions are being removed from solution. We're taking these ionic compounds and turning them into unionized water. We can measure concentration of acids and bases through a titration process. titration, we use a burette or similar instrument that will allow us to precisely add one liquid to another liquid, drop-wise, until we achieve a stoichiometric equivalence, so that all of one product is used up, all of both reactants are used up, and there's no excess of either one. To identify the end point, we usually use a chemical called an indicator. This chemical will change color along with the acidity or basicity of the solution, the pH of the solution. And if we pick the right indicator, then we get to the equivalence point, the stoichiometric equivalence point, and we'll be able to use the concentration of one of these solutions to help us determine the concentration of the other solution. By the end of the titration, we're going to have the volume of both solutions. We'll measure out the volume of one right from the beginning, and then we're adding the second solution in a controlled fashion that allows us to know the volume rather precisely. So if we have a concentration of one, then we can use it to calculate the concentration of the other. So for titration calculations, it's just another type of stoichiometric solution calculation. That means we're going to use molarity times volume to give us moles. Then we're going to use the coefficients from the balanced chemical equation to give us a stoichiometric ratio. That will give us moles of the other component, which is also molarity times volume. We can rearrange it to give us molarity times volume divided by coefficient will equal molarity times volume divided by coefficient. We need to know that balanced chemical reaction so we know these coefficients between the acid and the base.